I'd like to start my talk with giving you a brief introduction into chemical-induced thyroid disruption. Before I then will introduce my the project we're working towards a thyroid-liver chip platform to identify chemical-induced thyroid disruption on organ function level for both for rat and for human. At the end, I will summarize our work with summarizing some capabilities and limitations of the current system. You probably all know that the thyroid gland is an endocrine organ just below the larynx, and it's built of thyroid follicles, which are the key functional units. There's an epithelial layer of thyrocytes which form the follicle, and there's a follicular space like a lumen, which is filled with a protein called colloid-like solution. And one of the key proteins is thyroglobulin, which actually give rise to the thyroid hormones. Upon stimulation of the thyroid gland by thyroid-stimulating hormone TSH, which stems from the pituitary, the thyroid gland produces thyroid hormones T3 and T4, which are secreted into blood, and they are quite important for many different processes. The blood level is being reduced by the liver, who clears the hormones by conjugation reactions, and you will see this in a second. So once the blood level of hormones was lower, then the hypothalamus recognizes that, and via the pituitary releases thyroid stimulating hormones. And for anyone trying to form a functional thyroid model, it's important to understand that the follicular kind of morphology is an essential prerequisite, because the hormones itself, they are produced in the follicular space, and there are quite a complicated number of processes taking place, from components being uptaken from the blood into the lumen and then back. There's a number of different proposed mechanisms of chemical-induced thyroid disruptions, and the two most important ones is, for first, a direct inhibition of the synthesis of the hormones in the thyroid, and the second is an induction of an acceleration of the liver metabolism, so an increased clearance. The evidence for these effects primarily stems from either rodent studies or from in vitro assays, which cover single key molecular events, such as the inhibition of the thyroid peroxidase, a key enzyme. So chemical-induced thyroid disruption can give rise to several adverse effects, and the most important ones are thyroid follicular hypoplasia, up to cancer formations from a prolonged stimulation by thyroid-stimulating hormones. Another one is developmental neurotoxicity taking place when the blood levels is constantly low. Again, the evidence stems mostly from rodent studies. However, it's known that rodents are very sensitive to thyroid disruptions and may overpredict the potential risk for humans with regard to these adverse effects. This table here depicts key differences in the thyroid homeostasis between human and rat, and to give you one example, the half-life of the most prominent or most important hormone T4 is by a factor of approximately 10 different, so humans have a much longer half-life of the hormone. So these human species-specific features probably account also for the different sensitivities. We therefore aim to establish and characterize a thyroid liver chip for rat and human to identify thyroid disruption. I will also show you some feasibility data for both these direct effects on the thyroid and indirect effects. And we decided to use the tissues Humimic Chip 2 platform, as they can harbor both organ and bring them in one perfusion system. As we do not have a pituitary in here, of course, we had to supplement the TSH. Now to the data you can see here. Let's start with the rat thyroid model. We have isolated the follicles from fresh tissues, and we embedded the follicles into collagen and placed them into the chip. And we could nicely maintain the follicular architecture with the right polarity over at least 14 days. And upon stimulation with THAs, we could observe an increase in the second messenger C-amp, and we could also have a quite nice stimulation of the release of thyroid hormones. But you can also see that there was a slight decline over time. We did the same with the liver model, the rat liver model. We isolated freshly hepatocytes and non-parenchymal cells from fresh liver. We allowed them to form spheroids in ultra-low attachment plates, and then took the spheroids, embedded them in collagen, placed them into the chip. And again, over at least 14 days, we had this nice morphology and the right polarities you can see, and the release of albumin and urea, two of the liver-specific markers. And also, quite importantly, of course, for our project, those spheroids were able to, as a baseline, to conjugate supplemented T4 to glucuronidated form GT4, but we are unable to observe sulfation, which is the minor route of catabolism in the rat. So, but the major route was clearly present. Now switching to the human system, I can keep this briefly. We did more or less the same. We also, for the thyroid model on the left-hand side, we isolated the thyroid follicles from surgery material and embedded them into hydrogel and placed them in a chip. And you can here see, for example, in rat, the thyroglobulin, which is the key component in the lumen. We also saw CIMP increase and the release of thyroid hormone. But to our surprise, we observed a predominant release of T3 and not T4, and T4 is the physiological predominant form, and here in our model it is T3, but still we saw a nice and stable stimulation and release. With the liver, we utilize HepRG cells together with hepatic stellate cells, put them also into spheroids, so similar to the same with the rat, and found a nice release of albumin and, as we are talking about human, TBG, the thyroid binding globulin, which is the predominant binding protein in the human, which is absent in the rat. And another human-specific feature, we could see both routes of catabolism, the glucuronidation and the sulfation. Now, going back to the rat, we combined both tissues, and I can keep this short, so we experienced the same kind of performance, so no major differences when we either kept the tissues separately or connected them, which is a very nice finding. And most importantly, we did this feasibility study. I start with a direct disruption, so we added TPO inhibitors, MMI and PTU, which are supposed to suppress the synthesis of thyroid hormones, so we can nicely see a drop in the release of thyroid hormones, so a functional readout, but had no effect on the liver compartment. In contrast, when we added liver inducers to the system, so nucleoxynobatic receptor activators, we saw a nice increased stimulation in the accelerated catabolism of the thyroid hormone, here seen as a formation of GT4. But we could also see a slight drop in the endogenous T4, which we believe is just reflecting the increased or accelerated clearance of the endogenous hormones. With the human system, we also combined the system and could also see a sustained release of thyroid hormones for at least 21 days, and we could also, again, in combination, observed TBG and albumin release. However, we decided to first, in the human, to separately investigate the effects of reference compounds, so not in combination but separately. And for the thyroid, we could again see that also MMI, the TPO inhibitor, was able to reduce the release of thyroid hormones. However, for the liver system, we were unable to see like an induction of the catabolism similar to what we have observed in the rat, despite the fact that indeed we were successful in inducing the liver, as the phase 1 metabolism here depicted by cytochrome P450 activity was clearly induced. So this didn't work, and therefore we decided to modify the system. We worked or we replaced the hepatic compartment here, the HepRG cells by primary human hepatocytes. Did more or less the same. These preliminary data I'm showing here is still done in a static condition, so we don't have at the moment data for like chip culture. But what you can nicely see is then by replacing HepRG cells, the cell line, by primary human hepatocytes, we can clearly see an induction of the glucuronidation as well as sulfation of the thyroid hormones. Now coming to my summary already, so I could show that for the thyroid compartment, for both species we were able to maintain a follicular architecture and show a TSH-dependent release of thyroid hormones for at least 14 days. And for both species we provided feasibility data which allowed to detect direct thyroid perturbation, which can be monitored by a decreased secretion of thyroid hormones. For the liver compartment, with both species, we could maintain a functional liver spheroids for at least 14 days, which showed a baseline catabolism of thyroid hormones. And with both species, we at least have initial data, feasibility data, that we are also able to see these indirect mediated effects, the induction of thyroid hormone catabolism, which is like data package for the rat, of course, is more abundant compared to the human. And we could also see some species-specific features on the liver models, for example, the main route of catabolism, but as well species-specific responses on inducers. When it comes to the thyroid-liver combination, we have like a nice data package for the round model, which allowed to simultaneously detect direct and liver-mediated thyroid disruption in one assay at the same time, where for the human model we at the moment can only like keep them and have like basic functionality for 14 days, but at the moment we don't have data to demonstrate that similar also in the human we have the possibility to do both kind of mechanism in one system. But this is just a lack of data. It's not, I'm not telling that it's not working. We still have to work on that. But there are also a couple of limitations listed here. And therefore, it's clear that we are still in the process of optimization, at least the human system, and provide some feasibility data, which is still necessary before we can start with a more formal qualification with more reference compounds, which eventually, hopefully, will allow to at one point have an assay or a model which is fit for purpose in order to detect these kind of perturbations on the functional level in one assay, for example, also for regulatory purposes. Now I'm coming to the end. I'd like to acknowledge and thank many people who contributed here, and especially I would like to thank Diana Kavalat and Julia Kuhnlenz, which were like two former PhD students who did most of the experimental work of this project here. Julia is also here and will have a talk in the next session, so if you're interested to learn more, I can highly recommend to also listen to this second talk. And from this project we were able to compile two papers. The first one is already out and available at Altex, so if you're interested. The second one was just a couple of days ago accepted also in Altex and should be available in a couple of days. With this, I'm coming to an end. Thank you for your attention and happy to take any questions. Thanks very much.